Alrighty, howdy folks. So let's look at 2.7, section 2.7, which is about derivatives and rates of change. Let me give a bit of a motivation as to why, what's the big deal about all of this. The thing is, if you recall, I mentioned something like calculus is all about functions, right? First, when we were in high school, the way we understood functions was your teacher said, hey, boys and girls, if f of x equals x squared, what is f of 2? And that's 2 squared, which is 4, right? And then, well, what about if f of x equals 1 over x? And what is f of 2? Simple, 1 over 2. But what about f of 0? That's 1 over 0, which is undefined. So the function 1 over x was not defined at x equal to 0. So we needed to know this concept called being undefined, a function not being defined at a certain point. But then we said, wait, yes, it is true that at 0, 1 over x is not defined. But what happens if x gets closer and closer to 0? What happens to f then? That's when we needed the concept of limits. And now, another aspect of functions is what we are learning, which is whenever you say a function, y is a function of x, that means y depends on x. As x changes, y changes. But then the moment you say something changes, you are interested in at what rate does it change. For example, if you look at, let's say you're driving, and when you're driving and you're moving, obviously your position is changing, right? You are at one point at a particular time, a second later you are at a different point, and so on. But you are also interested in knowing how much your position is changing with time. If you're driving really fast, 1 second later you would have been further away, right? The position would have changed by a greater amount than if you were to be driving at a slow speed, right? So a rate of change is a very interesting and important thing to understand, and derivatives deal precisely with that. They deal with the rates of change. So, without much further ado, let's get into it. And here is the idea. The derivative of a function at a point A, and the derivative of a function f at a point A, and denoted as f prime of A. Okay, that f and with a hyphen is f prime of A, is the instantaneous rate of change of the function at that point. Instantaneous rate of change. I'll try to make all those things clear. And is given by f prime of A is this particular limit. Limit as h approaches 0 of f of A plus h minus f of A all over h. Okay. Limit as h approaches 0 of f of A plus h minus f of A over h, and that can also be written as limit as x approaches a of f of x minus f of A over x minus a. Okay. What do you mean these two are exactly the same? Yeah, they are. Suppose we were to say, we were to replace h with an x minus a. What is that? If we were to replace h with the x minus a, then what happens? We have h approaching 0 would mean x minus a approaches 0, and if you add a to both sides, that becomes x approaches a, right? That's exactly what we have here. And similarly, a plus x minus a simplifies to just x. And so we have f of x minus f of A over x minus A as x approaches A. So that's another definition of, this is another way of finding the f prime of a, the derivative of f at a. Cool? All right. Graphically, f prime of a represents the slope of the tangent of the graph y equals f of x drawn at a f of a. Whoa, what is that? Graphically, what does f prime of a represent? It represents the slope of a tangent, tangent to a graph. What exactly is the tangent of a graph? And where do you draw the tangent? At a and f of a. The x coordinate is a and the y coordinate is f of a. If you were to draw a tangent, then the slope of the tangent is precisely what we are talking about when we say f prime of a. Now, are you familiar with the tangent to a curve? Okay. I'm sure most of you are. If I asked you, hey, please come onto the board, and if I were to be teaching in a real classroom, and I said, hey, come and draw a tangent, and I draw a curve on the board and say, please draw a tangent at a certain point, and effortlessly you will come and draw a perfectly looking tangent. All of you, I know that. Okay, so I'm here to show you what the exact way of drawing a tangent is. I'm sure if I say, hey, can you draw a tangent at A? You will come and draw a line that kind of slopes like this. Right? Maybe I can show you. You will draw a line that looks like that. But is that the way to actually draw a tangent? Yes and no, not quite. So here is the idea. If you want to draw a tangent at x equal to a, then you need to pick a point B to the right of a. First, let's start with to the right. And B is one such point. Cool? And then you draw a line passing through A and B, which is this guy. Cool? So, is this the tangent line? No, it's not. Then what the heck is this line? Oh, this is what is called, anybody? The word starts with an S. It is a S-E-C-A. Got it? Secant line. Yes, this is not quite a tangent line, but it is a secant line. Now, what's with this? Well, when you want to know exactly at what rate this function is changing at A, what we have is an average rate of change to be whatever we picked up arbitrarily a point B to the right. So as we go from A to B, is there a change in y coordinate between these 2 points? Yep, whatever is the y coordinate of B minus the y coordinate of A divided by how much did this x itself change. That gives you an average rate of change of this of the function at the point A. Okay. By the way, this is all theoretical stuff. If you understand it, wonderful. If you don't understand it, hell won't break loose. But it's a good idea to understand, right? It's a conceptual thing. Okay, let me repeat. When we are looking at average rate of change at A, then we pick a point B and we say, what is the y value at B minus what is the y value at A, all over the x value at B minus x value at A. So that means the change in y divided by change in x. That's the average change. But as you can see, I can move that point. earlier I took the point B to be way over there, but I can allow that point to move. Now as I keep bringing that point closer and closer, the rate of change is changing, right? The slope of this secant line is changing. Now, as I bring B closer and closer to A, never ever making it equal to A though, then all these secant lines are approaching a particular line. Would you agree with that? Look at this. All these lines, secant lines, are approaching a particular line. And that line is what is called the tangent to the graph at that point. Right? That line. And that is an important way to understanding tangents. Now, having done that by picking a point to the left, what I really must do is I should be able to pick a point to the left, like here. Again, that is a secant line. That is, we cannot claim that to be a tangent line. That's a secant line. However, by bringing the point B closer and closer to A, now the secant lines are approaching a particular thing as a limit, and that line is our tangent line. Cool? Now check this out. In this case, whether we let B approach A from the right or from the left didn't matter. Eventually we got the same tangent line based on points to the right and points to the left. That need not always happen. But at least in this case it happened. And so, first thing, this is how you draw a tangent line. And the second thing, what is the derivative of the point at this, derivative of this function at this point? Whatever is the slope of this line. Whatever is the slope of the tangent line, that is the derivative at this point. As simple as that. Cool? So that's what I wanted to discuss with you. And let's continue. And as I've shown here, so if we draw a tangent line at A and f of A, and look at the slope of that tangent line, that slope is f prime of A. That's the derivative, is the point I made. Okay. Now, let's get to some problems. Find f prime of A given f of x equals 3x cubed minus 2x. Should that be somewhat straightforward? Yeah, it would be. Once you apply this formula or definition, f prime of A is limit of f of A plus h minus f of A over h as h approaches 0. So, given this, f of x to be 3x cubed minus 2x, let me ask you, would you know what f of A is? F of x equals 3x cubed minus 2x. What is f of A? 3a cubed minus 2a. You simply replace x with an a, right? Okay, can you figure out f of a plus h? Wherever you see x, you replace that with a plus h. As simple as that. So we have 3 times the quantity a plus h cubed. So you must take that entire a plus h and cube it. Minus 2 times the quantity, that means you enclose it in a parenthesis, a plus h, 2 times a plus h. Cool? Notice, that's exactly what I wrote. Making sure that I have the a plus h enclosed in parentheses. If you don't do that, then you would be making all kinds of mistakes. Similarly, here this a plus h must be enclosed in parentheses, because otherwise you will forget to distribute the 2 to both the terms. And also this minus, this subtraction thing, you have to distribute to both the terms here. Okay, so this stuff in this first square brackets is f of a plus h, and the stuff inside the second bracket is f of a and all over h. So how do we compute this limit? Patiently. You just have to multiply this whole thing and then subtract stuff and simplify and then evaluate the limit. Now, do you know the formula for a plus b, the quantity cube? A cube plus 3ab times a plus b cube. A cube plus 3a square b plus 3ab square plus b cube. So that's exactly what I did. A cube plus 3a square h plus 3a h square plus h cube minus 2 times the quantity a plus h. This. Right, now I'll distribute the 3 and well, I think I did this in my head. Let me show you what I did. I took this 3 times a cube, I get 3a cube, but then I recognized there is a minus 3a cube here, and that adds up to 0, so that term is gone. And we have a 9a square h. There is no such thing as another a square h, so just 9a square h. 9ah square, and there are no ah square terms, so I just wrote it. And then there's a 3h cube, which I wrote. There's a minus 2a, but then there is a plus 2a. What do you mean, man? There's no plus 2a, that's a minus 2a. Well, isn't there a minus sign here? So minus negative 2a, that becomes plus 2a. Or subtracting a negative quantity is the same as adding the positive quantity. So minus 2a plus 2a, that adds up to 0, and we are left with a minus 2h. We've already accounted for these two. This minus 3a cube cancelled with this 3a cube, and this positive 2a cancelled with this negative 2a. So that's what we end up with. Okay, are we in a position to figuring out the limit yet? Not quite. If we plug in h equal to 0, then the top becomes 0 and the bottom also becomes 0. We have 0 over 0, which is an indeterminate form. Oh, but wait a minute. Can we not factor an h out of the top? And if we do, can we not now h over h is 1? Can we not do that? Yep. And so we have limit of just this stuff inside the parenthesis. Okay. Now can we apply the limit? That means plug h equal to 0 into this. Yes, we get 9a square from the first term. The second term goes to 0 because there's a multiplication by 0. 3h square also goes to 0, but we still have minus 2. So this simply reduces to 9a square minus 2. You follow that? That's it. So patiently doing algebra is what it takes when you have to compute the derivative at a point. Given a function like this, that's what it takes. I'll solve plenty of examples just so that you are crystal clear about the whole thing. Okay? Next, find f prime of a given f of x is 4 over square root of 1 minus x. The procedure is again the same. We'll apply this f prime of a equals this definition, limit of f of a plus h minus f of a over h as h approaches 0, and f of a plus h. Would you agree? This is what you would have. What did I do? Wherever I saw x, I replaced a plus h. That's how I got f of a plus h. And then wherever I saw x, I replaced with an a, and that's how I got f of a. So f of a plus h minus f of a is what I have on the top over h. So how do we evaluate this limit? If we plug h equal to 0, then we get 4 over square root of 1 minus a minus 4 over square root of 1 minus a, that is 0 over 0. 0 over 0 is an indeterminate form. So we have to do something to this. So what I did is I first subtracted the fractions. Okay. And there is a certain way that I add or subtract fractions. What I've done is I have posted in iLearn some background material, and in that I have videos of how to find LCM, how to find GCF, and how to factor quadratic, and one of them is how to add fractions. So please first watch how to find LCM, the least common multiple, which becomes the common denominator, and then watch how to add fractions. I know you might be thinking, oh, come on, man. I know how to add fractions. Yes, I'm sure you do. But please watch it, because I do it in a slightly different way from how you learned in high school. And I think my way of doing helps a lot. Okay? All right. So when you apply that method and subtract fractions, this is what you end up with. But then if you plug in h equal to 0 into this, once again, I have a feeling, yep, you end up with a 0 over 0. So what do we do here? We in fact solved problems of this kind previously. Any thoughts? You gotta multiply by the conjugate. You multiply the top and bottom by square root of 1 minus a plus square root of 1 minus a minus h. And when you do that, this is in the form of a minus b times a plus b, which is a square minus b square. Right? Do you agree with that? This thing is a minus b times a plus b, which is a square minus b square, which means the square roots disappear and you just get 1 minus a minus 1 minus a minus h, like this. And I didn't touch the denominator, I just left it the way it is. Cool? And now we notice that if we simplify this, 1 minus 1, oh, that is 0, minus a plus a, that also is 0, minus negative h is positive h. So there is a 4h, 4 times h on the top. That's what the whole top reduces to, a 4h. And in the bottom, I still have the same thing. But then these h's, we can divide them. And so this reduces to 4 over all of this. Now we are in a position to substituting h equal to 0. And when we do that, this becomes square root of 1 minus a and times square root of 1 minus a. Square root of 1 minus a times square root of 1 minus a is just 1 minus a. And we have square root of 1 minus a plus square root of 1 minus a. What is that equal to? Let me repeat that. What is square root of 1 minus a plus square root of 1 minus a? What is p plus p? 2p. What is q plus q? 2q. So what is square root of 1 minus a plus square root of 1 minus a? 2 times square root of 1 minus a. Right? As simple as that. So we have 1 minus a, this times this is 1 minus a, 2 times the quantity square root of 1 minus a. What is 1 minus a times square root of 1 minus a? Can we write it in a slightly different way? Does that look like a to the m times a to the n equals a to the m plus n? 1 minus a, the quantity raised to 1 plus 1/2. Right? Square root can be thought of as a power of 1/2. So when I did that, and also I reduced 2 goes, I divided both the top and the bottom by 2, and so the top became 4 over 2 is 2, and 2 over 2 is 1, and 1 minus a, the quantity raised to 3/2. 1 minus a, the quantity raised to 1 plus 1/2, which is 3/2. Right? Algebra was a bit hard on this one, but as such the concept was fairly straightforward. Okay, so be sure to practice a lot. Next, find the equation of the tangent to the curve f of x equals 3x cubed minus 2x at a equals 1. Find the equation of a tangent? How do we find that? How do we find the equation of a tangent to a curve? Do you remember what's called the slope point form, right, of a line? Y minus y1 equals m times x minus x1, right? Okay, what is m? Slope. Slope of what? Slope of the line. What line are we talking about here? The tangent line. Can we find the slope of the tangent line? Yeah, we can, because that slope of a tangent line is nothing but our derivative. We know how to find derivatives of functions at certain point, at a point. So we will invoke that result and figure out what the slope of the tangent line should be. And once we do that, we also know the point itself. Wait a minute, do we really know the point? What is this? A equals 1. That means x equals 1. Okay, if you know x to be 1, can you figure out y? That is, y is f of x. Can you figure out y? Yeah, just plug in a value of 1 for x. 3 times 1 cubed minus 2 times 1. So that's 3 minus 2 is 1. Oh, you mean they want to the point is 1 comma 1? Yep, it is. So at 1 comma 1, what is the tangent line's equation? The tangent that you draw for this curve, what is its equation is the question. So let's apply m equals f prime of a. Now check this out. What? Wow, I'm mighty clever. Earlier we solved this problem, 3x cubed minus 2x, and at some point a, what is the derivative? Well, we got 9a squared minus 2. So if a happens to be 1, the slope of the tangent line is just f prime of that a equals 1, f prime of 1, and so all we need to do is plug 1 for a. If we didn't know this m to be f prime of a to be 9a squared minus 2, we would have to compute the limit and all that stuff. But since we already have that result, I'm using that result. And so it turns out m equals 7. The slope of the tangent line is 7. And to find it, we use the slope point form, for which we need the coordinates of the point. And how do you find that? A equals 1, that is x equals 1 in this case. So I just plugged in x equals 1, and turns out, like this is what I was talking about, f of 1 is 1. So that means the point is 1, 1. And what's the slope point form? Y minus y1 equals m times x minus x1. What is x1 here? The x coordinate of the point, which is 1. What is y1 here? The y coordinate of the point, which is also 1. So y minus 1 equals, m happens to be 7, that's the derivative, right? And so 7 times x minus 1. So y minus 7x equals, if you simplify it, you get negative 7 plus 1 on the right hand side. And so that's negative 6. Cool. So now we can apparently find the equations of tangent lines to curves at whatever point we are asked. That's the beauty of this. Okay. Now, I told you that I have this habit of giving engineering examples, right? I'm going to give you an engineering example right now. Are you familiar with something called a milling cutter? Milling cutter is kind of a cylindrical cutter. It's kind of like a router. Are you familiar with a router that carpenters use? Or can I think of another example? Lawnmower. Okay, lawnmower blade, as it spins, it cuts a path, right? And so this milling cutter is something that you use to cut a path, usually on a metal or wood. So when you cut that, it looks something like this. So let me animate that for you. That cutter is spinning, and as it spins and moves, it starts to cut the material along its path. All right. And when I was working on my master's degree, I had a course on computer-aided machining, and we learned how to write programs that would on CNCs, computer numerical control machines. And one of the questions my professors asked was, if a milling cutter is milling a parabola y equals x squared like this, right? So as you saw, that milling cutter, the whole idea was that it needs to cut a profile of y equals x squared. And his question was, when the milling cutter is cutting this y equals x squared, and it is, say, cutting at x equals 2, y equals 4, what is the position of the center of the cutter? Right? Folks, if you understand what I'm talking about, fine. If you don't, equally fine. Okay, don't sweat it. For those who are curious, I just want to show you this. So the question was, find the location of the center of the milling cutter when it is milling a parabola y equals x squared at 2, 4. So like this. That point A is 2, 4. And let's say this milling cutter has a radius of 1 inch. Then what is the position of B at that time? Okay. And I think I got lucky on that one. Somehow I got the idea as to what it is that I needed to do, and I solved the problem. Why am I talking about that in your class at this time? Well, that's because I used exactly the concept that we just discussed. That is, the derivative of the function is the slope of the tangent. So what I did is, I needed some angles that I needed to figure out. So to figure out these angles, I drew a tangent to the curve at 2, 4 and figured out what the slope of the tangent is. And I'm sure did you learn this already, or maybe, I don't know. Did you know the slope of the tangent is same thing as tangent theta? You know the trig function tangent? So tangent of theta gives you the slope of the tangent. And that theta is the angle between the x-axis and the tangent itself, measured from the positive x-axis to the tangent. So I could figure out the slope of the curve at that point using the derivative, and then that meant I knew the tangent of theta, from which I can get theta. And once I knew theta, I could do one more, just a bit of geometry, and I could get this. So I redrew the figure here, and as you can see, I know the point A to be 2, 4, and this angle to be theta, which I can find, and that means this is 90 minus theta, and using trig, I figured out that the b sub x, the x coordinate of this point B, should be whatever is the x coordinate here plus this horizontal distance of AC, which is r times cosine of 90 minus theta, where r is the radius. Okay, and that turns out to be a sub x plus r sine theta, and similarly the y coordinate is a sub y minus r cosine theta, meaning whatever is the y coordinate of this point minus r times cosine theta. You see? Now, the only reason I could successfully do this problem is not because I'm somehow smart or anything like that. It's just that I remembered the concept of what a derivative actually is, that it is the slope of the tangent drawn through the curve at a point. That's the concept I used here. Cool. That's it, folks.